Right. Let's explore in this video the notion of science and its uses of measurements. The act of doing science involves many different things. The design of experiments, comparison of one's results to others' results that are out there, formulation of hypotheses. But one of the tasks that a scientist always is involved in is the taking of measurements. And there are guidelines and rules about these measurements that we need to be familiar with and use throughout our high school chemistry course. Let's start with a basic definition of what measurements are all about. I think these definitions that are provided you are pretty darn good. A measurement is a type of observation simply. When you go outside in the morning or during the day and you say, look, the sky is blue, I feel rather chilly, I need to put a jacket on. Those are measurements, but we refer to them as simply qualitative measurements. They're addressing a quality about nature that you are observing. On the other hand, if you say there is a wavelength of 357 nanometers coming from the sky and the temperature is a cold 3 degrees Celsius, what you're offering there are quantitative measurements or numbers associated with the observation. And both of those type of measurements do get used in all sciences and have value. In any measurement, there are limitations to it. There's an error or uncertainty. If you measure the distance that you travel as you go from school to home, that number is going to vary from day to day at a minimum because you did not take exactly the same path, but also the particular instrument that you used would matter. If you used a meter stick versus used perhaps a laser measuring system, you're going to get different numbers. And so there's a error or uncertainty in part to how you made the measurement or instrument that you used. Regardless of the error or uncertainty, you do have to indicate the units that are being used. If you are measuring the distance from home to school, you're not going to record the numbers in grams, for example, or in degrees Celsius, because the instrument that was being used was measuring distance and not mass or thermometer that was measuring the temperature. Finally, the limits of the measurement are based upon the skill that the person brings to the task. If you ask a 4-year-old to measure the distance from home to school, that person is going to come up with a little bit of a different answer than if you're asked, for example, a surveyor. So the skill set and the instrument used, those all set limits to how accurately you can come up with a number, and we get better and better at it in the world of science, but there's always going to be a built-in error. Now let's take a look at this here. This is now getting into an interesting concept. The bar that is in green, that is what we want to measure, and the brown below is the ruler. Now you'll notice that the ruler is set up by increments of 1, 2, 3, 4, but also there's a midpoint indicated, the smaller hash, and that's a 0.5. Now if you want to measure the green bar, we want to measure it one level of precision beyond the marking. So you'll notice that we have a 4, a 4.5, and a 5. Now the green bar falls between the 4.5 and the 5. And what we're able to do is we can actually estimate that the number would be 4.82 since we can actually indicate the 0.8 is solid and then estimate beyond that. Here's yet another example. This is on a graduated cylinder. You will notice that the increments 35, and you can go up the lines to get to 40. Now yes, it is expected of you as a person to be able to figure out that each of the smaller hash is worth a value of 1. And the way you do that, you just simply count it and check it. So if you count the small lines, it's 35, 36, 37, 38, 39, right. 40 is where it gets you. Now what we do is we estimate the last value. And so what we come up with is 36.3. That is the limit of the instrument that we use. Now if you change to different instruments, you get different degrees of precision. And what we mean by precision here is the degree that the increments can go. So if you rank these rulers, you will notice that B is the least precise because the intervals are in units of 100. Now if you go to D, you'll notice that the distance from 0 to 100 is the same as it was in B. However, the D ruler has the halfway mark indicated. Therefore, it's broken distance down into smaller increments, and it gives you a greater precision. A is further subdivided from there, and A and E are in fact the same level of precision. Bit of a trickster there, because what has been provided in E is the number 50 between 0 and 100. But the actual distance 0 to 50 in E is in fact the same distance it is in A. We just didn't label the 50 mark. So just because you wrote the number in doesn't make it more precise. It depends upon the increment that's getting used. And of course C would have the greatest precision since it does provide the smallest unit or increment. And as we can see, the Muppets do have a very, very accurate degree of precision with their measurement. Now we said whenever you make a measurement, there is always an error or a degree of error that gets made. And these errors matter a lot to us. There are two broad categories that measurements can have mistakes made in. And the use of the target here helps us get a grasp of it. You'll notice that the yellow in the middle, that's the target. That is the correct measurement. And you'll notice on the left that the targeting or the shooting to get to that target is very nicely clustered. So those measurements would be considered very close to each other. The problem is that all of them are off the mark. All of them miss the distance. So these are referred to as systematic errors, and the result is an imperfection in the equipment technique. What would be an example of that? Well, let's measure the distance from your home to school. And you get out a meter stick and you start to measure it. Well, you're going to come up with a number. And you could argue that we could have those numbers every time you measure that distance. Let's suggest that those measurements come out fairly close to each other. You go, right, we must have a good measurement of that distance. But in fact, your brother or sister the night before needed a piece of wood to do a project, and they hacked off part of the meter stick. The result is every time you measured the distance from home to school, you got roughly the right number. The problem is the instrument used was wrong. It was compromised. It was damaged. It wasn't giving you an accurate reading. The result is you have a consistent measurement every time you make it, but the actual measurement you get is way off because it's not accurate. The second type that you do is called a random error. So let's take an actual working meter stick. You tape it back together after it being cut by your brother or sister, and so you now have a true meter stick. And let's measure the distance from home to school again. And every time you do it, you get kind of different results. And that's because you take a slightly wider turn at one portion of the route, and perhaps you cut across the grass to shorten your distance once or twice because you were late. And the result is that every time you measure that distance, it's really, really scattered. And those referred to as random errors. And you know there are random errors involved because when you make the measurement again and again, those numbers just do not come back properly. And again, there could be an equipment error or a technique error, but you know it's random errors because there's a scattering of your numbers. And if your numbers come back consistently roughly the same, you have nice consistency, but the answer itself may be scattered, and that's referred to as a systematic error. How can I reduce these type of errors? Well, if you want to reduce systematic errors, you make sure you take patience and make the measurement carefully, and more importantly, the measuring tool is in proper working order, and your brother or sister didn't cut the meter stick partly down. In terms of random errors, one way to reduce the effect is you can get an average among the various measurements, and you can create a better tool that would reduce the scattering that goes on. For example, use a laser measuring system as opposed to simply a meter stick. Now, that leads to the following. These are two definitions. Accuracy is how close you get to the actual target. Precision is a degree to which every time you make the measurement, they're close to each other. And that produces four different possibilities. In this quadrant, which is very elegant, you have the following. If you have imprecise or random errors, and you have systematic errors, you get what we refer to as an inaccurate, imprecise result. You'll notice that the green shots are all in the upper left-hand side. So they are somewhat clustered, but they are all off the mark. Therefore, they are considered imprecise. If it is accurate, then in fact you get the cluster around the actual answer, but it's pretty scattered. On the lower left, you will notice there's good precision, meaning that each time you make the measurement, they're very close to each other, but they're far away from the actual measurement itself. And of course, the lower right is ideal. It is accurate because it is very close to the actual value you were seeking, and it's precise because your numbers after each measurement are very consistent. However, this fine young lady or man is not very happy due to the lack of precision and accuracy. Now, once you've made measurements we often have to run calculations with them. And again, there are limits to what you can do in the calculation of these measurements. To begin with, we must record our measurements using what's referred to as a scientific notation. What that does is it takes numbers and reduces them or changes them to a consistent appearance. So we always in a scientific notation have the number followed by a decimal followed by the values after it. It's always a single digit followed by the decimal. And so we move the decimal in the upper example 3 places to get 5.983, and then we say times 10 to the third. In scientific notation, do we ever use a different base other than 10? No, it's always 10. And you'll see lower down, we move it to the right to get 3.4 times 10 to the minus fourth. And you must keep straight that when you move the value or decimal to the left or to the right, that you get a positive exponent or a negative exponent. And the rule says move the decimal to the left, it's to a positive decimal. If you move the decimal to the right, it's a negative decimal. So here are your conversions. 8.96 times 10 to the fifth, you can convert that to the whole number as you see it. If you got 1.07 times 10 to the minus fourth, you can change it to the number below. Now this is the more common way you're going to see things. You're going to take a number, 562, and convert it to scientific notation. 5.62 times 10 to the second, and B 0.0038 converted to 3.8 times 10 to the third. So those are the conversions to scientific notation. Now, what do I do? What's the operational approach that I take in working with scientific notation? Your strategy is as follows. 5.0 times 10 to the third times 2.5 times 10 to the fourth. Your strategy is you sum the exponents, so it's 10 to the fifth, and then you simply multiply the two values together, and that gives you 12.5 times 10 to the seventh. The way to think about it is these are two separate events. You add up the exponents, and then you multiply these two values here. Your last move is to then convert 12.5 times 10 to the fifth, 12.5 times 10 to the seventh, and you convert them to 1.25 times 10 to the eighth. So multiplication, you add exponents. When you divide exponents, as you see here, it's 10 to the third, you subtract them. So 10 to the third minus a negative 7 is the same as 3 plus 10 to the seventh, and therefore you get 10 to the 10th. Then you take 8.2 divided by 2, you get 4.1. And so those are the rules of operation when you deal with scientific notation. Now, we have one last idea. Always keep calm, and you want to always pay attention to SigFigs. Now, what do you mean by SigFigs? Here's the situation. You and your buddies, there's 3 of you, have been studying all night for chemistry. And you know you need a big cup of coffee to stay awake before you take the chem test. So here's your problem right here. You've got 2,468.5 milliliters of coffee. There's 3 of you, and you want to divide it up equally. So you got 2,468.5 divided into 3 equal parts, and you punch it in the calculator, and you get 822.8333333 milliliters. You can't do that because the measurement of the volume only went to the tenths place. And your answer goes way out to here. Your answer exceeds what in fact your measurement was at. So you're going to have to do a rounding off. And what you would say is you get 822.8 milliliters and you have to stop there. So taking a look at SigFigs, there's a degree of accuracy or exactness, a precision to the measurement. And you have to go to within the first digit that got estimated. So what happens is you get 45.872. This is the estimated value. So SigFigs are the limit that the instrument gives you. So you got 3 SigFigs here. Even though there's a 0 here, it's called captured. And so there are 3 SigFigs here. Now notice, because a decimal point was placed here, decimal point, it makes these zeros relevant. So there are 3 SigFigs here, 4 here, 5 SigFigs here. Now, what happens is the 0 here gives you and defines this decimal point. So there's only 2 SigFigs here. There are 2 here, and there are a total of 3 here. Here you have 4 SigFigs. You again keep your 4 SigFigs times 10 to the third. Here you have 2 SigFigs, so when you convert to scientific notation, it's 3.4 times 10 to the minus 4th SigFigs. When it comes to rounding, 4 or less you round down. That's a very common rule. 6 or up you round up. And what we do is when it comes to the 5, we round up if the value is 5. And this person is very happy that this is done.